here it is. So Robert, please.
Okay, thank you very much. Good morning, everyone. Thanks for being here on a Friday morning after a pretty intensive week of lectures and discussions. So I think you must be exhausted. So I'll try to go easy today with my last lecture, and I'm trying to kind of get to the point of the main and critical questions that we are dealing with in research today. So kind of the final frontier of ab initio calculations that we try to push further and further nowadays. And a lot of that has to do with these keywords that I have in the title of my fourth lecture, namely precision, uncertainties, and we'll see how much more along these lines we can discuss. I'll first go back to the end of the third lecture where we discussed in medium SRG and kind of an upgrade or a hybrid construction of the in medium SRG and the no-core model. Since this was a bit quick, I will go through part of this again, and this will end up or lead us to the motivation for this precision or uncertainty questions that I'll address afterwards. So as for the other lectures as well, please make active use of the chat or interrupt me and ask questions. So I think that has worked really well for the previous lectures. So please keep going like that. So in medium NCSM, this was our hybrid, our combination of in medium SRG and NCSM. And just to remind you, the key idea of all of these medium math methods, couple cluster and in medium SRG, is decoupling. So you want to kind of isolate a small part of the Hilbert space, in the extreme case, just a single state from the rest of your Hilbert space. So you suppress all kinds of excitations, and you can think of particle Hall excitations in this context, so that you kind of pre-diagonalize your Hamiltonian, at least partially, at least with respect to a single state or a small reference space. And for these decoupling approaches, there are various mathematical tools to achieve this decoupling transformation. And the tool we use in the SRG and the in medium SRG is the underlying similarity RG flow equation here. And this flow equation looks very simple. We discussed it extensively in the free space situation. So when we just evolve 2 or 3 body matrix elements of the Hamiltonian, and you even had a chance to do that yourself in our little project. Now we use it in a many-body context. So the Hamiltonian here is really the A-body Hamilton matrix, if you like. And the idea is to really, at the A-body level, implement this decoupling, and that amounts automatically to a solution of the eigenvalue problem for selected states. Now, if we don't want to isolate completely one of the states, the ground state typically, but isolate kind of a little subspace, a tiny, tiny model space, which we call reference space, from the rest by suppressing these off-diagonal matrix elements here, then this is kind of an ideal situation for a secondary calculation after this flow equation, a secondary no-core model type calculation, which then diagonalizes the problem in this tiny space and yields a whole set of structure information, not only ground state energy, but you get excited states from that as well, and you get wave functions so that you can compute other observables, radii, electromagnetic transitions, all this kind of zoo or portfolio of spectroscopic observables. So therefore, it's such a nice and efficient combination. Use this in medium SRG to pre-diagonalize or block diagonalize your Hamiltonian, and then use the no-core model in a second step. And this is what I've kind of listed here. That's kind of the flow chart of the calculation, how it goes. You typically start from a tiny NCSM calculation just to define the reference state and this little reference space, which is, say, something like an n max equals 0 no-core shell model space. So that's super small. And you can construct these spaces and solve the eigenvalue problems for defining the reference state in those tiny spaces for essentially each and every nucleus of the nuclear chart. Then you use the medium SRG to decouple this tiny reference space from all of the rest of your Hilbert space. Because your reference state now itself has many determinants in there, it's a small, but a larger than one space, you need an extension, you need what we call the multi-reference in medium SRG. And this is a technical step, which is non-trivial if you look at it in details. And we use generalizations of normal ordering and Wick theorem, which come from quantum chemistry in order to define this multi-reference version of the in-medium SRG. But in the end, conceptually, it's exactly the same as before. The difference now is we don't use this single corner matrix element, which represents our ground state energy in the single reference in medium SRG. We use a matrix that comes out of this evolution and do a secondary NCSM calculation in the end. And this then provides all the observables we want. So in a sense, this is the many-body calculation, and this is another pre-processing step, like the free space SRG that we did in the very beginning. But this pre-processing step now really acts in the specific A-body system, in our specific A-body Hilbert space for the nucleus of choice. So it's a very nucleus-specific optimization or pre-diagonalization, if you like. And so these two things work really well together. And I illustrated that with these flow pictures once again for the example of carbon-12. As function of this in medium SRG flow parameter, which runs along this axis, we can transform the Hamiltonian. And just to show something, I monitor the zero-body piece of the Hamiltonian, and that shows this characteristic behavior that it drops with flow parameter and then briefly stabilizes. But this is not the interesting bit. What's really interesting is now the behavior of the Hamilton matrix itself throughout this flow evolution. And you see exactly what we wanted the transformation to do does really happen. So this is my original Hamiltonian for this carbon-12 problem. And the little reference space, which is simply the n max 0 NCSM space that I discussed, that's this little block here. And if you just watch what happens throughout the evolution, this block becomes more visible, and this off-diagonal coupling part, which connects this block to all of the rest, that's suppressed. So if this were completely absent, zero matrix elements everywhere, then it would be absolutely sufficient to solve the eigenvalue problem of this little matrix, and you would be done, because this little block would not talk to the rest of the Hilbert space anymore. So that would be another n max 0 calculation, and you would be done. And you can try that. And if we just do NCSM calculations, these are now the secondary calculations afterwards, once we have the transformed matrices, you can do the n max 0 calculation, which is the blue symbols here. And you can also, just for fun, go to larger n maxes, here up to n max 8. And you see for the initial Hamiltonian, we have this very bad and difficult convergence behavior with increasing model space size. So you're not able to extract some meaningful statement about the ground state energy, even some extrapolation based on this data. But if you go later in your flow evolution and you pick out a matrix, say at this regime for the flow parameters, you see that the convergence is essentially instantaneous. So from n max 0 on, you are at your converged number for the ground state energy. And of course, this is due to the fact that you've isolated, decoupled this n max 0 block. So this is something which makes which maps our big NCSM problem, namely the basis dimension, to a different problem. We handle this via the in-medium SRG evolution and can live with tiny spaces in our diagonalization. Now there's a question, could you use multi-reference in-medium SRG to build effective interactions for shell model calculations with a certain inert core? Yes, you can, and that's done. That's actually not done with a multi-reference in-medium SRG, but you could. That's a very clever idea, and I think it would be good to do that with multi-reference. We are thinking about stuff like that. But what has been done also very successfully and in very different and broad applications is to use the single reference version, so the standard in-medium SRG, to evolve an Hamiltonian for your core nucleus, so the core that you want to use later in your shell model calculation, and extract from this evolution by a specific choice of the generator, which actually does this shell model-like decoupling. So you decouple the valence space information, valence space orbitals, and the matrix elements that connect valence space to either core states or the excluded space above. So you use a setup for the generator which suppresses essentially all these couplings of valence space with the rest. And you map that into the matrix elements of the Hamiltonian, just like this picture here. So if you imagine this would be your valence space in a shell model calculation, then you want to do the same. You want to decouple from core and excluded orbitals. And this is being done, and that works very well. And it's kind of still a bit tricky if you go far away from your core system. So if you really want to go to mid-shell nuclei in a large shell, then you start to see effects of multibody induced terms. Again, we cut everything at this normal order two-body level. You will see some effects of these higher order terms, just like you see it here. We mentioned that last time, that if you go too far in the flow, you might promote lots of contributions into these omitted normal order three-body, four-body, five-body terms, which are formally there, but which we've truncated. And the same thing happens for the shell model, so there's still room for improvement, but this has been very successful. And I think that's a very, very elegant approach to connect valence space shell model calculations to this ab initio world. You know? So I think that's a very clever idea. Now, this is, of course, a huge help. Just need to do Nmax 0 calculations, but you shouldn't go too far, because things can go wrong with this flow due to these omitted terms. So you have an extra source of uncertainty, and you see this extra uncertainty already here. I compare now my converged in medium NCSM result, which are these points, with a dashed line, which is from a standard NCSM calculation without in medium SRG, without this normal ordering, two-body approximation. And you see that there is some difference in the predicted ground state energy, which is due to this normal order two-body approximation of the initial Hamiltonian and this truncation of the flow equation. So you kind of get additional uncertainties through this extra truncations, which is to be expected, really. Now, you can do that for essentially many nuclei. We are just exploring the SD shell with these methods. Here just another example, oxygen 20, which shows a really nice flow behavior. So you see out here, nothing happens anymore. So your results are stable with flow parameters. So there you don't have this problem with induced many-body terms. And you are converged at Nmax 0, which makes these calculations super cheap compared to this dashed line here, which is again the full NCSM calculation for oxygen 20, which is heavy. Yeah? So this is really a big simplification and a great saving in terms of computational effort. You get quantitative results. Here, the summary for the ground state energies of the oxygen isotopes, which are at the 1 to 2% level in agreement with your best possible straight NCSM calculations. And this 1 to 2%, that's illustrated here by the comparison of these green symbols, which are the simple in medium NCSM, and the blue symbols, which are the NCSM with a natural orbital basis. And the best calculation really are those light blue symbols, because they are NCSM calculations with the explicit three-body force, no approximation regarding normal ordering also in the game. And you see that if you go from the light blue symbols to here, you have a slight overbinding. And this is due to the two instances where you kind of employ this normal order two-body approximation. First, for your initial Hamiltonian, and that brings you from the light blue to the dark blue symbols. And then second time during your in medium SRG flow evolution, and that gets you to the green symbols. And this is kind of this 2% span that we typically quote as an intrinsic uncertainty of these medium math methods when it's applied just for a given Hamiltonian. Yeah. And this is extremely good in comparison to agreement among different ab initio methods that we had in the past. So a lot has happened in terms of development and refinement of many-body methods to reach this kind of intrinsic accuracy. And this brings us to a point where one can really now distinguish effects or discrepancies in comparison to experiment, whether they are just because of a pure many-body treatment, because we are too simplistic with our truncations, or the uncertainties due to truncations are too large, or whether discrepancies result from your initial choice of the interaction, from this chiral EFT input that you use. And this is kind of an important step or milestone. So, and this was really how the community worked over the past, say, decade or so. The first phase was really improvement of many-body technology, pushing calculations to larger particle numbers and better accuracy. And we are now at a point where I would say we have done a great job with these methods, and we have a lot of tools at our disposal, and we have the impression, at least from comparisons among different methods and estimates of missing terms, stuff like that, that we have the many-body uncertainties under control to this 2% level. But now it's a point to ask, what's about the Hamiltonian? And that's the thing that I want to discuss in the main part of this lecture. Just to complete this here, in addition to ground state energies, since it is in the end an NCSM calculation, you can do the same analysis for excited states. So you can do these flow pictures also for here the 2+ excitation energy in carbon 12. So this is now just the difference between ground state and excitation energy. The colored symbols are again NCSM calculations for different Nmax with the in medium SRG evolved Hamiltonians. And you see that essentially from the beginning, these excitation energies from very, very early on in the flow, they are rather stable. Not too much happens, but something happens. And you see that here in this regime, because before the problem starts with induced many-body terms, you have a nice and stable result, which happens to be in very good agreement with experiment, which is this dashed line here. If you go to oxygen 20, you see that there is some kind of convergence behavior. So you change a bit for the original Hamiltonian, and this is reduced. So you're more stable with respect to Nmax if you go to the evolved Hamiltonian. But in general, I mean, there are little effects on the excitation energies, and that has been known for a long time. Excitation energies are difference quantities, and they converge in a classical NCSM calculation much faster than ground state or absolute energies. So this helps you. Therefore, there are also calculations of excitation energies being published where there's no chance whatsoever to converge the ground state, because the excitation energies, these energy differences are more stable with respect to Nmax. So you can use this method, the medium NCSM, to compute spectra and to compute the complete spectroscopy. That means also all the transitions, electromagnetic moments. It requires that you treat all the operators that you need consistently, also in this in-medium evolution. So if you want to compute, say, a quadrupole moment, you have to evolve the quadrupole operator as well through this in-medium SRG scheme. This is more tricky because quadrupole operator is a rank 2 tensor, so it's not a scalar operator anymore. So that causes extra computational effort, but it's possible and we do that. So in this way, you can address all the observables that you can also compute in the standard NCSM. And here is now just a little side-by-side comparison for different carbon and oxygen isotopes. And if you just compare the right-hand panel for the NCSM and the left-hand side for the in-medium NCSM, whenever the NCSM results are stable, you have a pretty good, or we would say excellent, agreement with the in-medium NCSM calculations. There are some exceptions, some states which move quite a bit. For example, the 0+ here in carbon-16, that's somewhere completely different. And also this 0+ in carbon-12. So this 0+ is famous. That's the so-called Hoyle state. It's a strongly alpha cluster dominated state. And this is notoriously difficult to describe in an harmonic oscillator basis. Even the in-medium NCSM has problems, and because these bars, which are shown here, they indicate, so to say, the variation of the position of this state if you change the flow parameter out in this plateau region where nothing is supposed to happen anymore. So you see there's also something difficult in the in-medium SRG world. And in the NCSM, this state doesn't even show up because it's up here. Oh, no, it's up here. Sorry, that's the one. So you see tricky states, which are tricky because of their structure, remain tricky in the medium NCSM, because in the end it uses the same underlying basis. So you don't really have much of a gain in terms of describing cluster structures, for example. Okay, now a quick summary of this whole in-medium SRG chapter. I find this method is absolutely fascinating. It has lots of pros here. It is super flexible. And you've seen that already because we have used the same SRG idea for the free space pre-processing of the Hamiltonian, and now in a single reference and a multi-reference version, also in combination with NCSM. So you can do lots of things simply because the basic formulation, this flow equation, is so simple. And all the physics is encoded in the generator. So whatever you want to do, you can typically achieve via a clever choice of the generators that you put in. It is very straightforward to extend to open shell nuclei in this multi-reference formulation, and this is very different from coupled cluster. So there you have a much harder time to do that. You get immediately a Hermitian Hamiltonian at any point of your flow, which is great because you can use it in a secondary calculation like the NCSM, as we did. And as we discussed already, it's also a bridge to the valence space shell model in the sense that we talked about. So this is a very nice extra use. It's easy to access other observables. It has the same goodies as coupled cluster theory in terms of scaling with particle number, size extensivity, and efficiency compared to a particle hole scheme. There are, well, two maybe cons. It's also not variational. You've seen that we tend to overbind ground states because of these higher order, normal order terms. And if you want to include them, so goes to something like a normal order 3 body approximation, which would still be an approximation. It's not complete there because the medium flow will include even higher particle rank terms. But this needs a little more work. That's getting tricky. The full flow equations are probably too hard to solve, but we are working on kind of lowest order corrections to handle these normal ordered induced three-body terms. Okay. So are there questions, more questions on these methods themselves? Because now I will leave the discussion of the methods and go more to the results. And as advertised here, I want to talk a little bit about the limitations of ab initio methods today.
Could you give a concrete idea of the computational
Okay.
cost?
Yes.
A few real examples.
Yeah. Let's take, say, this oxygen 20. If you want to do the straight NCSM calculation in, say, Nmax 8, Nmax 10, with all the bells and whistles, so with natural orbital basis and this importance truncation, you're typically thinking of a calculation which needs dozens up to, yeah, say 60 or so cores on a, not cores, nodes on a large memory computer. So the limitation for the NCSM part, if you reach something like Nmax 10, is clearly the storage for Hamilton matrices, and you need 1, 2, 3 terabytes of main memory accumulated over your different nodes for that. So we have a very nice machine in Darmstadt which has exceptionally large main memory on the individual nodes. So this is a calculation which would nowadays be done on, say, 16 or 32 nodes. In the past, we used thousands of nodes for this calculation. So this is really, really heavy. You cannot do that in your kind of desktop or workstation environment.
And how long does it take, typically? Say,
it doesn't take too long, because once you have so many nodes, in order to accumulate all the RAM, you have so many processors, it typically takes 12 to 24 hours in total. So that's not too long. So that's wall time. Yeah. This one can be run all the way on a single computer. I mean, for the in-medium SRG evolution, we don't even bother to put that onto different nodes. So we don't even parallelize the code in an MPI fashion. It's OpenMP parallel, of course, but this runs, say, 24 hours on a single node for the in-medium SRG evolution. And then just depends how far you want to go with your final Nmax calculation. If you stay at Nmax 2, which is good for ground state energies, for example, this is a run which you can again do on a single node, essentially. So it's a huge saving. Still, I mean, if you think of, well, that's great, now we go to heavier nuclei, maybe we go to, say, tin isotopes directly, then even these Nmax 0 spaces or Nmax 2 spaces get very, very large. So in the end, even these tiny Nmaxes are challenging. So there is still the limitation in mass number, and the limitation still results from the matrix sizes that you have to handle in the NCSM part of the calculation. Yeah. So it will not go all the way to the heavy nuclei with this method. We are just now working on calcium isotopes, just to give you an example, in something like Nmax 2 and sometimes Nmax 4, that still works. And we'll have to see how much further we can get with this. Okay, more questions? Good. Yeah, let's talk about the limits. And the limits are maybe surprising. Here is a summary of the best possible coupled cluster calculation for ground state energies. We did that already a while ago, but it was kind of a very important revelation, if you like, for us. This funny acronym here determines the coupled cluster truncation level. So we discussed CCSD, coupled cluster singles doubles, which can be done easily. And then the next step would be the inclusion of triples. So 3-particle, 3-hole excitations in this exponential ansatz, which cannot be done fully. So that you use approximate schemes to include these triples effects. And without going into details, this completely renormalized couple cluster 2-3 is, I think, one of the best schemes for the inclusion of approximate triples corrections. So this is state-of-the-art couple cluster in nuclear physics. What you see here is just for a large range of nuclei from oxygen 16 to tin 132, the ground state energies that we computed with this best possible couple cluster approach here with a chiral 2+3 nucleon interaction. And it's the chiral 2+3 nucleon interaction that I essentially used for all the examples before. And this interaction we used for a very, very long time because, as I've shown you before, it does a very nice job in the oxygen isotopes. So the oxygen ground state energy for oxygen 16, oxygen 24, these red symbols is in very nice agreement with the experiment, which is represented by this bar. Down here, if you're wondering, this just shows you how big the triples correction is. So how much of an effect this correction for the three-hole excitations in the exponent does. So it's not really big. So you see it's 0.2 or so MeV per nucleon, but this is kind of the level of precision we are working at. So this is, from the many-body point of view, a very accurate calculation. It's as accurate all the way to the tin isotopes. So in terms of computational accuracy when treating the many-body problem, we are not really limited to light or medium mass nuclei. You can go to substantial mass numbers already with these methods without losing kind of accuracy or computational reach in the solution of your many-body problem. But you see that the problem comes from somewhere else. The agreement is very nice with the experiment in this oxygen region, but as soon as you end up, say, in the calcium isotopes here, you see something goes systematically wrong. So we have something like 1 MeV per nucleon overbinding as compared to experiment for these calcium isotopes. And it only gets worse, something like 1.5 to 2 MeV per nucleon if you go to the tin isotopes. So this is now really where the problem is. We are happy and accurate enough with a many-body calculation itself, with a solution of the Schrödinger equation. But now we have to worry about the Hamiltonians that we are using. Obviously, this particular chiral Hamiltonian that I've used here is not suitable, not accurate for the description of these heavy nuclei. You get significant overbinding. And really, the effect here, this difference, is much larger than this thing here, which could serve as an estimate for the many-body uncertainty. If you are really conservative and say, okay, I've truncated this couple cluster series and I take the step from doubles to triples as my measure for many-body uncertainty, then this 0.2 MeV per nucleon would be it. And it's out of the question that this 1.5 MeV per nucleon cannot be due to many-body uncertainties. So there's really a problem with the Hamiltonian. And this is seen also in other calculations. This was now a couple cluster. We can have a look at in medium SRG calculations, and these are now open shell isotopes included. This is the full calcium isotopic chain with the same interaction. Let's just look at the panel down here. The panel up here is if you just keep the initial chiral two-body force. We don't need to discuss this. I just want to keep the full Hamiltonian, which means initial chiral 2 plus 3-body interaction. And you get these red results here for the calcium isotopes all the way from calcium 34 to 62, sorry. This is a multi-reference in medium SRG version, one specific flavor that I didn't discuss. This is based on Hartree-Fock-Bogol-Lyubov particle number projected ground state, and you put the multi-reference in medium SRG on top of this. So this gives you access to essentially this semi-magic isotopic chain, so spherical isotopes, but You can go away from the closed shells. And what you see here is kind of the same picture. You develop this overbinding as compared to experiment with mass number. And there are two types of calculations. These red symbols are the multi-reference in medium SRG that I just described, and these orange boxes for closed or closed subshell isotopes are, again, this couple cluster CRCC23 calculations. And you see they agree very, very nicely. Again, even in this mass range, we can benchmark different methods against each other and show that we have very good control over our many-body treatment, so that this kind of discrepancy has to come from the Hamiltonian. Okay, there's one more question. Do you calculate the matrix elements of these interactions, chiral two-nucleon interaction, or are these already available, like you gave us for exercises? No, yes, good question. We calculate them ourselves, at least at the level of the basis representations, the SRG stuff that we use here. Typically, the chiral two-nucleon interactions are provided by those groups that develop these interactions as a little Fortran package, which gives you partial wave momentum space matrix elements. So you can simply write to Ruprecht Machleit or Evgeny Appelbaum and ask them for this or that interaction, and you will get a little Fortran code which computes for given angular momentum quantum numbers, momentum space matrix elements of the two-body force. And you can then go from there and put it into the basis representation you like, do the SRG, and so on. It's a little bit different for the three-body forces, because there the matrix elements are so complicated that you cannot simply compute them in a little Fortran code. So these Fortran codes really do the computation of the matrix elements based on all the formal expressions in your chiral EFT calculation from scratch. You cannot do that for the three-body. That's too expensive. So for the three-body matrix elements, you really start to ship around some representation of the three-body forces, just like the ones that I gave you. But this is not done by the interaction makers. This is done by the many-body people like us. So for the three-body part, we had to do much more development work for the matrix elements ourselves. But in principle, if you want to work with something like that, just talk to the people, and usually you will be able to get a set of matrix elements for your developments or your applications. Okay, now we have to worry about interactions, and this is kind of the starting point for my last section or my last lecture. It's this question of precision and uncertainties. And let's start with the question, or just say a reminder, or going back to the beginning, and the question, with these chiral interactions, what have we done so far, in particular with the interaction that I used for all the illustrations up to this point? And what can we do better from this chiral EFT perspective? And that's the question of chiral interactions for precision calculations. Let's go back a little bit of a history again on the development of chiral interactions that have been used in many-body calculations. So this is now, I wrote here, incomplete and totally biased. It's biased really from my perspective as a many-body person. So there is definitely more history to chiral EFT interactions than this. But for me, the kind of real impact of chiral forces on many-body calculations starts here in 2007, where there were first calculations of p-shell nuclei, including a chiral three-nucleon interaction, were published. So these were NCSM calculations in an old framework with Lee Suzuki transformation and so on. But it was really the first application of chiral three-body forces beyond the few-body sector, so beyond 3 and 4 particle systems. And this is where really the potential of nuclear structure calculations with these forces became evident. And this is really the first generation of interactions. So I quantify it here in terms of generations. This was just driven by what can you do technically. It's not driven by, we try to do the best thing from the chiral EFT perspective, but we just do the thing we can. And these calculations were based on one of the first chiral 3-nucleon interactions by Entem and Machleit at N3lo, and they were combined with a chiral 2-nucleon interaction at N2lo with a completely different regulator. So this was kind of patchwork, if you like. But it did work, and it was kind of the trigger for many more investigations that went through the 2010s. So we did at some point SRG transformations for these forces. And then 2014, we saw what I just showed you, namely that you have this overbinding beyond oxygen isotopes. And something else happened, which I didn't show you yet. You get catastrophic description of nuclear radii with these interactions. So at that point, it became clear that something has to be done with respect to the chiral inputs that we use. And then there is kind of a second generation where one first tried to fix things, fix these problems by, well, some kind of, well, you try to inform your interaction by using many-body observables, for example. But you discover once you do that, you sacrifice something at another end. One set of interactions, or one interaction that was used quite heavily, is the so-called N2lo Sub Interaction. This is designed with many-body observables in mind. So you look at something like radii and energies of, say, oxygen isotopes, and you tune your interaction to do a good job there. But when you do that, you discover that you have to sacrifice something. And in this particular case, the Oak Ridge people had to sacrifice the accuracy of the phase shift description. Actually, this interaction does a terrible job on the two-body phase shifts. So that's a radical departure from the paradigm of using realistic interactions, if you want. Because, okay, you fit to many body observables, but you cannot describe the phase shifts as good as before. Actually, you can only describe them for extremely low energies, something like 0 to 30 MeV, where you usually do an excellent job up to 300 MeV in scattering energies. So this was not really satisfactory. And at that point, one might ask, okay, is there a fundamental problem, or are we just not including something properly? And as a result of this kind of thinking, the third generation of chiral interaction started, and it's still being developed. So we are far from being done there. And the third generation really takes the chiral input more seriously. In particular, things like power counting and systematicity are treated more rigorously. And at the same time, you try to assess uncertainties that come from the modeling of your interaction. And since, well, we are supposed to be in a beautiful place now, if this school would happen in person, so I couldn't stop but think of this part as Renaissance, because we are really kind of discovering a few old ideas and bringing them to new beauty. This thing was kind of the Middle Ages, where you did something which you shouldn't be doing. And this were the glory old days, antiquity, where you started with this business. So we are now in a Renaissance, if you like, with respect to the development of these chiral interactions. And I want to illustrate a bit what that really means. I showed this picture, or a different version of it, before. That's just the table of diagrams, pictorial representation, if you like, of contributions to the chiral interaction, sorted by chiral order. So the power in your power counting scheme, some exponent in terms of a small quantity, and in terms of the particle number, the rank of these interactions, 2-body, 3-body, 4-body interaction. And if you take this kind of map as something to illustrate how interactions were designed, then the antiquity story, so the first generations of interactions, they did typically take a favorite 2-nucleon interaction at some chiral order with some cutoff, and you added your favorite 3-nucleon interaction at N2lo because you couldn't do better with some cutoffs, and you ignore the theory uncertainties and the inherent consistency of the chiral scheme. And one of the typical interactions, this first one that I used throughout the talk, that's of this type. So you use N3lo up to 2-body forces up to N3lo, 3-body forces only this first contribution at N2lo, different regulator schemes, different cutoffs, so nothing of a consistent interaction. And if you're desperate and are looking for reasons why things don't work, you might question this step. You might want to be more consistent, more rigorous from the good underlying theory point of view when you deal with interactions. And this interaction, just another illustration, does produce the problems with binding energies in this medium mass regime. And here I show for the first time also the radii for these medium mass isotopes. You see, even in the oxygen isotopes, you predict point proton RMS radii or charge radii, if you like, that are smaller than experiment. And this difference is already quite significant. It sounds like a little number, it's 0.3 Fermi, too small. But if you convert that in densities in your nucleus, then this means that your density in the center of the nucleus is almost twice as large as it should be as nuclear matter density. So this is not really a good description of a ground state, although the energy itself looks quite nice. And it's only getting worse if you go to heavier systems. So there's something systematically wrong with these interactions, as we've already mentioned. Now, can you do better? Well, from the formal point of view, this map, you would say, okay, let's take this whole chiral power counting, the different orders and the systematicity seriously. Don't patchwork interactions, but just go level by level. And not just go to the highest level that you can possibly handle, but really do all the levels and observe how your results change with order of your chiral interaction. Use the systematicity that you have in chiral EFT to do step-by-step, order-by-order calculations, because this will give you an information on the convergence behavior of this chiral input. And that's super important information because there are truncations, there are uncertainties, and you would like to estimate how big these uncertainties are before claiming that you agree with experiment or you disagree with experiment. This is something which was never done in these first 2 generations of forces, and we are only starting to do that now. So this order by order paradigm and the consistency within an order is important. Now you see, N2lo is something obviously that can be done because we have the 3-body force at N2lo already, and restricting the 2-body force to N2lo, that's easy peasy, you can do that. N3lo is a very different story because you need lots of additional 3-body terms, and they only have been worked out at the level of matrix elements recently. In principle, you also need 4-body terms, which is super painful. But actually, that has been done. We've done that. In principle, we have done calculations which even have some 4-body forces at N3lo. Luckily, we convinced ourselves that these are small, so we don't really include them if you want to do medium mass calculations. But we do include 2- and 3-body forces consistently at N3lo. And this is now something which goes into a systematic development. So we use 2- and 3-nucleon interaction with consistent orders and cutoff schemes and values. You can vary the chiral order and the cutoff to assess uncertainties. And there are additional knobs you can play with. You can explore the dependence of choice of regulator scheme, as we call it. So all these points here, this, for example, this is a contact interaction, this as well. So this is a delta function if you think in position space, or it's a constant if you think in momentum space. So you have to kind of cut off this contribution, otherwise it's infinite. So this is what is behind this regularization scheme, and there are different options for that. And this might have an impact on your many-body results as well. And this has to be investigated. And we have a first kind of family of interactions which follows this paradigm, goes up to N2lo, starting from leading order, step by step, including the three-body forces, same regulator scheme, same cutoffs. So as consistent as you can get. And there are other schemes being developed now. So essentially all of the interaction makers are embarking onto this and providing the whole series of interactions at different orders, which is kind of necessary input for these studies. If you do that, then this picture changes. And that's now kind of jumping to the end of a story, which I'll explain in a minute. The green symbols here are your first generation calculations from before. These open symbols and the blue and the red symbols are now new generation, third generation calculations for next to leading order. That's these open symbols here. N2lo, that's the blue symbols, and N3lo, that's the red symbols. And you see things have changed quite a bit. Suddenly, all these points are exactly on experiment for the binding energy, and suddenly the radii work. So you are spot on for the radii, even in the calcium isotopes, for example. So this is a big difference to the original picture with our interactions. We can obviously, by treating the underlying chiral EFT stuff better, improve on the description of our medium mass systems quite a bit. Now I jumped many steps in the discussion. So let's go slowly. How can you achieve that? And there's one little trick in there, which you might like or might not like. And this is something I want to discuss now, but I have to dive a little bit deeper into the construction and the optimization of these chiral interactions.
Excuse me, so I have a small question there. Could you please go back to the last slide? There seems to be some sort of a underbinding for the nickel 78 case. Is that because it's doubly magic?
No, I mean, this is, I will come to the uncertainties of these calculations later. This is a calculation where I would say that the many-body part is not yet fully converged. So one of the truncation parameters is not pushed far enough in order to converge this nickel 78 nucleus. So I think a large part of this is really due to many-body discrepancies, not due to the interaction. There's one other thing one has to be careful with. If you go extremely neutron-rich, 1 degree of freedom or one type of physics that we haven't considered at all so far becomes relevant, and this is continuum coupling. So for these very neutron-rich systems, close to drip line, beyond drip line, you can expect that the basis expansion, which is rooted in an harmonic oscillator, is still not good enough. You want to couple to some continuum degrees of freedom, and this will lower energies as well. So this is kind of in the extreme neutron-rich region, something that you typically observe. And I mean, here, don't worry about that point. We will come to the uncertainties in a minute, and I'll show you what kind of many-body truncations we address and we vary in order to assess these uncertainties. And there you will see the parameter which is critical for these very heavy nuclei. And actually, this is the reason why I didn't go further than these nickel isotopes in this plot. You could easily do the same calculations technically for tin isotopes, but then you would have to go even further in this many-body truncation parameter, which we haven't done yet. Yeah.
Okay, sir. Thank you very much.
Mm-hmm. Okay, more questions. So that's in principle a good point to ask for that.
Well, just a quick thing. So in the last slide, so actually in the old calculation, let's say mixing orders damaged one much more than just doing it, let's say, with all orders consistently. Is that right?
Well, I think it's not so much about the orders. So the big effect from here to here, in particular for the radii, is not due to the order of the three-body force, so this mixing that you described, but it's rather the choice of regulator for the three-body force. So in this old force, the two-body force was using a non-local regularization scheme, and the three-body force was using a local regularization. Here we use non-local for both of them. And actually it turns out that for the radii, and I'll show that, the big effect from here to here is really due to the switch to the non-local regularization of the three-body force. And this is something that we don't fully understand yet. So why this big difference? That's a little bit of a mystery. And it's also concerning in some sense, because you would expect this regulator stuff to be purely technical, and you hope that it doesn't have any impact on observables. This is obviously not true. Therefore, this regulator choice is kind of a big question now. How to motivate that better, or what the right or the wrong choice could be, whether one has to decide it based on many-body results, or whether there is some altogether better approach to that. So, but I will show that in a little example as well.
Okay, thank you.
Okay, now let's go slowly. Let's go step by step. What has to be done in order to construct such a family of interactions? Number one, you start from two nucleon interactions. And as we discussed earlier, this is kind of the domain of a few people, a few research groups that have specialized in construction of chiral interactions. And essentially there are two or three of them, not many. One of them is a group around Ruprecht Machleit. So he is famous in the interaction business. He's the father of the Bonn interactions, ABC, CD Bonn. And then he constructed one of the first chiral two-body interactions at N2lo that was widely used. And he and his colleagues, they have provided an updated version of interactions, not only N2lo, but actually from leading order to N4lo. I only use them up to N2lo here, with a non-local regularization scheme, different values of the cutoff, and they are all super accurate in the reproduction of two-body data. So two-body observables, deuteron properties, all the nucleon scattering data up to 300 MeV are reproduced very well by these interactions. So that's essentially a compendium that encapsulates all the good two-body physics that you want to have. It's super realistic in that sense. But typically these groups, as I also mentioned, they don't do the work of including or designing the appropriate three-body interactions. That's more done by the many-body practitioners. So that's our job. So we supplemented these two-body interactions by the corresponding non-local three-nucleon interactions at N2lo and N3lo. So we went up to N3lo with the three-body force, used non-local regulators, used the same cutoff values as in the two-body force to be kind of as consistent, systematic as possible. Now, when you start with the three-body forces, essentially many things are fixed from the beginning. So the three-body forces contain a number of low energy constants, parameters, that are already present in the two-body force and that are already fixed through the determination of the two-body force. However, there are two parameters left, two new contact terms which only appear at three-body, and it's two in both orders, N2lo and N3lo. So that's a lucky coincidence for us, because we are able to handle two parameters. Otherwise, you would have to devise really a massive kind of optimization and fitting framework, and that has been done for simultaneous fits of the two-body and three-body interaction. This is something that the Oak Ridge group with lots of collaborators has pioneered, and this is essentially where these N2lo Sub interactions come from. But we don't do that. We just stick to the original two-body force and supplement the three-body force and determine these two low energy constants, which are called CE and CD. It doesn't matter where they come from for the moment. There are two of them, and typically they are determined in the few body systems. So for example, using the triton binding energy. And we typically do the same, at least for one of them, the CE, which is the three-body contact interaction, which shows up in N2lo for the first time. This one is determined from the triton binding energy. So whatever I do, all the interactions that I design will reproduce the triton ground state energy. The second parameter, however, we do something different than in the past. Typically, you would also try to determine that in few body systems, maybe with some beta decay half-life of the triton that was done, or with properties of helium-4. For now, we keep it as a parameter. So essentially, we construct a whole family of interactions for each order with different CD parameters. And the CE for each CD is always fixed to reproduce the triton binding energy. There's a question, if NN already reproduced data, does not adding 3N on top degrade agreement? So when it reproduces data, then it means NN data, two-body data, all the information you have from the two-nucleon system. And you cannot degrade that by adding a three-body force, because the three-body force doesn't act in a two-nucleon system. It's a different story if you just look at a calculation with a two-body force for a heavy nucleus and find that this is in good agreement. Then you might well ask this question. And actually, this is relevant because the two-body forces alone don't do such a bad job, actually. We'll see that. So the main point, or our kind of change in strategy, was we start to play with the CD parameter and see what different choices of CD give us in terms of observables of different nuclei. You can start playing this game for helium-4. So this is kind of the simplest nucleus beyond the three-body system. And this is now a very complicated plot, but it's a plot that we heavily use to understand and interpret what's happening. What's shown here for the N2lo and the N3lo interactions is the ground state energy of helium-4 on this axis and the proton root mean square radius on this axis. And these curves, which look like tilted parabolae, they are just results of calculations for a given Hamiltonian. And this Hamiltonian gives you 1 point in this energy radius plane. And the different points are different values of the CD parameter. So I will run through a whole range of CD parameters and get different answers for ground state energy and radii for all of these Hamiltonians. And they are very, very systematic in this kind of parabolic shape. These dashed lines mark the experimental data point for energy and radius of helium-4. So you see, you're kind of describing a trajectory in this plane, which kind of passes by this experimental point. So the first message is, if you construct your three-body force, it's not guaranteed that you can reproduce something like the four-body system, helium-4, in energy and radius precisely. You cannot, because this trajectory doesn't pass through this point. So you cannot determine or pick up an interaction, a combination of parameters, which does a perfect job on helium-4. Same for N3lo. Here, this parabola is moved to the left, and you see you never even get a point where you could reproduce the ground state energy of helium-4 exactly. So here you have 2 points, here and here, where you get the ground state energy correct, but not the radius. Here's a point where you get the radius, but not the ground state energy. In this case, you cannot get either of the two exactly. So you have to keep in mind that even in these few body systems, you don't have absolute freedom. So there are strong limitations due to your chiral EFT model of the force. Of course, even N2lo is missing stuff. So we don't have the four-body force here, which would first show up in helium-4. Maybe this brings us from here to here. Or I need still higher orders. Or this is just for a single cutoff choice. If I use different cutoffs, this picture changes. These parabolas shift around and the situation is different. So even if you want to determine everything at the few body level, and this is kind of pure religion, if you like, in this chiral EFT world, determine interaction in the few body sector, use it in the many body calculations and see what you get. Even if you do that, even in the few body world alone, you don't have the perfect description. So you should really start to think about, is this a problem, or is this maybe all within uncertainties of my whole scheme? The chiral EFT expansion induces an uncertainty. You shouldn't expect perfect agreement because you don't have the full theory. The many-body calculation has uncertainties. So this, once you start this, you have to really start to think about uncertainties at all levels of your calculation. Now, you can do the same game in a many-body calculation. And this we did here. That's again my full lineup of nuclei up to the nickel isotopes, ground state energies per nucleon and radii. And now I do this variation of the CD, low energy constant, in many body systems. No problem. I mean, each one gives me a different interaction, and I do calculations for all interactions. And what you see here is, of course, you can change the energy of medium mass nuclei via the CD parameter. You can pick something like sweet spot, which would be this red symbols here. That's the one I showed before, and that's for a CD parameter of +4. At the same time, you see that the radii are good all the time. So they seem to not depend significantly on your CD choice. And they are more or less correct whatever you do. This was very surprising when we saw that, because it relates to the question from before. Now we do consistent N2lo plus N2lo, and the radii are correct all the time, irrespective of CD. So why are they suddenly correct? Is this better matching of the orders or something else? And when we saw that, really, we said, okay, we want to do many body calculations. We are not interested exclusively in few body physics. So why not take the liberty to tune this CD parameter once and for all in a many body system? And we simply chose the oxygen-16 ground state energy instead of some helium-4 or triton beta decay or whatever to fix the CD parameter. And this is leading to the interactions I showed you before. So essentially, we depart a little bit from the pure wisdom of chiral EFT. We don't do stuff in the few body sector anymore. We use one datum of the many body world to fix our interaction. Turns out that we don't do any damage in the few body world. The thing is simply, if you do fits in few body systems, you have a very long lever arm up to the medium mass. So any tiny change in few body might induce a big change in a heavy nucleus. So therefore, it's kind of much more robust if you do this fit in a heavy nucleus. The few body result will not change much, but you get automatically a much better description in your medium mass regime. So if you like, that's a little bit moving towards a paradigm of effective or phenomenological interactions and density functional theory. Maybe we can discuss that more in the discussion session later. There are still significant differences, but this is kind of one of the tricks that we used. Go to oxygen-16 to determine this CD parameter. Okay, but there's one more part to the story, and I only show that because we had this discussion already. Actually, the fact that the radii always come out well has to do with the choice of the regulator for the 3 nucleon interactions. Here we used the non-local regulator for the 3 nucleon interaction. And in all of the other older interactions, for technical, purely technical reasons, one used a local 3 nucleon regulator. And actually, you can try to now play the same game that I did here with a local 3 nucleon force. So I use N2lo now only to be consistent in the orders. And I combine my non-local 2-body force with a local 3-body force and do the same game fixing the oxygen 16 ground state energy. And you see it doesn't work. It doesn't work for the energies. So you have oxygen 16, right? Oxygen 24 is kind of okay, but then you see again the old overbinding that we've discussed before. And the radii are too small all the way. So the 3 nucleon regulator has a big impact, and that's kind of surprising. And this we still need to understand. So that's kind of an open issue and a topic for discussion even today. Okay, now we have to talk about uncertainties now. Any more questions before we start that?
Can you, when you showed your change, say with the CD in the heavy nuclei, can you go back and show what is the effect of this going from -3 to +4, and we say in the 3-body sector? You already showed that, but if you can go back now and illustrate here. What is
okay. Yes, good point. Thank you. So this is a plot which we have to look at for the helium-4 system. And we look at the cutoff, which corresponds to this blue line here. So forget the others. I can go back one more, then I only have the blue line. Okay. So if you would do this optimization for helium-4, then kind of the best compromise to get energy and radius okay would be this point here, which is CD equal 2. Now I extracted from the oxygen 16 result, I should go to CD equal 4, so this point. So that means I do overbind helium-4, but the radius is pretty okay. So it is overbound already for this best possible few body fit. That's something you have to keep in mind. And it's only getting worse by something like 400 keV from here to here. So you really do not do big damage, but it might be surprising for some that you cannot, even without any freedom in choosing this parameter, you can choose whatever you like, you will never get the ground state energy correctly. No? But it's a small effect, it's this 2 to 4. And actually what I don't show here, this is a calculation for the bare interaction, no SRG evolution. If you do an SRG evolution, you have to think about these induced many-body terms, because we only do SRG up to the 3-body level. And for some miraculous reason, if you don't include 4-body induced terms and higher, this point moves over here. So actually, if you use the SRG evolved calculation for the few body systems, the results look much better, but it's kind of an accident or coincidence because it's due to the induced many-body terms that you've omitted that the results become better. Yeah. That's also a very puzzling thing, which we didn't understand really so far. So if you take the point of view, I always use SRG evolved interactions, that's my starting point, then the situation is much better than this one, because then your point is somewhere here. So this is pretty new stuff. So we published that last year. So there's lots of things still to be kind of explored and understood. Okay, and one of them, before worrying about all of this, one should really look at uncertainties of your approaches. And uncertainties are now everywhere. And this is really a point which I want to make, and that will be more or less my last point. But when asking all these questions that we've discussed now, why is this so and so much off experiment? Is that good? Is that bad? Stop worrying or stop this discussion until you've quantified how big the theory uncertainties in your approach really are. So theory uncertainties come in at each and every step of our way. It starts from the Hamiltonian, from the chiral EFT, from the truncation of this expansion at a certain order, from choice of regulators. All of this are uncertainties which are induced or generated at the very first step of your calculation. But that's not the last source. If you go through some SRG preconditioning, the free space SRG, as we just discussed, you truncate at some point, you don't include induced four-body forces, for example. That causes uncertainties. And then, only then, you embark into your many-body solution, which has, depending on the scheme that you use, again, lots of different truncations, approximations, and thus lots of different sources of uncertainties. In principle, you have to be honest and go through each and every of these steps and each and every of the sources of uncertainties and at least try to quantify how much this truncation affects your final observable. You want to have a theory error bar for your final energy or your final radius, which takes into account all this mess that has happened in between. All the mess that has happened from this pure Schrödinger equation, or even before that, because this already contains all the choices you've made for the interaction. So this is obviously, without any practical example, a very tedious job. It requires many more calculations than just getting your single number for the ground state energy of oxygen 16. And it requires much more work in terms of analysis. And this is kind of the point where the community, the ab initio community now is, and many different groups are working on different aspects of this uncertainty quantification problem. There are real experts which are diving into the questions related to the Hamiltonian. Of course, everybody who has a many-body method tries to quantify many-body uncertainties, but I think it's still some way to go to have the real comprehensive picture and a standard, say, approach to quantify the complete uncertainties in your calculations. I think nowadays there's not a single complete quantification, but we are all heavily working towards it. And I just want to give you an idea what goes into this. So what different effects you have to take into account and you have to address to arrive at such a total uncertainty. It starts with the interaction. So we discussed that now we have different orders in this chiral expansion available. So that allows us to look into the convergence pattern of this chiral expansion, starting from leading order, which is not even shown here, to next to leading order, and N2lo and N3lo. And this is probably the segment of uncertainty quantification which is best developed at the moment. There are different kind of approaches, prescriptions to extract an uncertainty for this chiral truncation from the order by order behavior of this chiral expansion. Here I just use a kind of simple prescription, which however can be traced back and related to Bayesian methods for uncertainty quantification. We've developed that in the so-called LENPIC collaboration, which is very focused on development of new interactions. In the meantime, we do that really in a Bayesian framework, so you can use sophisticated statistical methods to address this. But what we do here is just a simplified protocol, which is based on this power series character of the chiral expansion. So you have a small parameter, which is a momentum scale, which is called Q, and that's defined by a typical momentum of your system divided by the breakdown scale of your theory, which is around about 600 MeV, and this number Q is typically 1/3. So that is luckily smaller than 1, but it's not super small. And in order to kind of make an estimate of all the missing higher order terms in your expansion or in your power series, you just look at the changes between subsequent orders that you've actually calculated. And you can weigh these changes by powers of the small parameter, that's this Q, and you just use this kind of pattern of convergence to estimate the residual uncertainty at some given order. So this is kind of an explicit formula for the uncertainty at order N3lo, which has all the differences to the previous orders weighted by higher, by successive powers of the small parameter. And you look back all the way to leading order. And if you do that, you get these colored bands here. The red band is for the N3lo calculation, and the blue band is for the N2lo calculation. And you see, just from looking at the order by order results explicitly, this looks really nice. So you have bands which are nested, so they get smaller and smaller, and they are consistent with each other. So they overlap, and that's always a good sign. And you see that the accuracy you get from this single source of uncertainty at N3lo is actually quite nice. At N2lo, you would say, okay, that's, if you look at the radius, that's, the band has almost half a Fermi width here. That might be a bit, not really precision, not really satisfactory. So from this, you would already conclude that it's a really good idea to go through to N3lo with your method, with your interaction, to have sufficient accuracy. And then it really looks quite convincing with this little red band here. But don't forget, that's just one of very, very many different sources. And this is something that we kind of routinely quantify nowadays. But it's not the end. Of course, you have your many-body framework behind all that. And these calculations I use here, they are from the in-medium SRG. So the first thing you can study in this in-medium SRG framework in terms of many-body uncertainties is your model space choice. So you can choose different truncations for your single particle basis. This is this little Emax parameter, and I show here results for Emax 12 and 14. And I just compare these results to each other to estimate whether this is sufficiently converged in this parameter or whether I should assign a finite uncertainty to that. And there's a second parameter, which is actually much more critical than the single particle energy, which just tells you how many single particle states you really use in your calculation. There's this parameter which we dubbed at some point E3 max. It's a capital E. In our syntax, that means it refers to a beyond single particle truncation. And that's an extra truncation for the three-body matrix elements that essentially everybody is using. Again, it's for purely technical reasons, because if you don't use that, there are too many matrix elements in the three-body interaction to store it. It's getting too hard to handle the three-body forces. And actually, this is a critical piece of limitation, if you like, if you go to heavier systems. And this is illustrated if you look out here. So essentially, for all these different truncations, everything looks nice and on top of each other up to the calcium isotopes. But if you go into the heavier nickel isotopes, and that's the issue we discussed before, you see suddenly things change. So here the blue symbols, which are the only calculation which has this Emax 14 parameter, so that's a pretty restrictive truncation on the three-body force, that is off. And if you go with the same two-body with the same single particle basis size to larger E3 max 16 and 18, that's the red and the purple symbols here, you see that comes down. And actually that's the reason for the problem that we discussed before with nickel 78. There in particular, you see that you have a big effect of this E3 max cut, and you should probably go even further than this E3 max 18, which is kind of state of the art. So we did that a while ago already, and still it's very hard to go beyond this because of number of matrix elements. But you see that if going heavy, you might want to go still lower in energy with still larger values of the three-body truncation. So these are really nitty-gritty details which you might forget about, but this ends up in your total uncertainty budget. And that's the reason why we don't go beyond these nickel isotopes, because then this effect is not controlled, or this truncation is not converged anymore. Now, there is more. For example, the flow parameter of the free space SRG. We truncated away the four-body induced terms in free space SRG, so there might be an effect. We have to study that, and we study that by varying the flow parameter. And you see again, down here, nothing changes, not much changes here. Up here again, you have a little effect. So you have a little sensitivity to these omitted SRG-induced four-body terms. All of this has to be kind of added up. And there are more things which we didn't even show here, and that's mainly what I discussed before. This N2B approximation of the initial Hamiltonian and of the in medium SRG flow equations also causes an uncertainty. And from comparison to the no-Cauchy model, this is what we discussed before, we would estimate some 2% effect. And this dominates, at least up to the calcium isotopes, all of these other many-body uncertainties that I've shown. So for now, we can just take this 2% as a dominant uncertainty in our many-body treatment. And we add that to the interaction uncertainties that we have before. Now here's an upgraded version of the picture from before for all of these closed shell isotopes from oxygen to nickel. This is what we looked at before. One cutoff, 500 MeV. Now I added the other cutoffs for the interaction, 450 and 550. And you see the picture is in nice agreement with experiment for all of the cutoffs. You see some systematic trend in the size of these uncertainty bands. They decrease if you go to increasing cutoff. And you can see it even in the raw convergence pattern. The N2lo calculations here, the open symbols, are further away from the rest in the soft interaction, and they are closer to the rest in the harder interaction. So this is kind of what drives this change in the uncertainty band. But this is only now the interaction uncertainty. Let's add these 2% many-body uncertainties, and then we arrive at this kind of bands. And this is what we can do. So if you are honest about your uncertainties in your treatment, if you insist on going from the initial Schrödinger equation and collecting all the errors that you make on the way through truncations into an error band, then this is what you would get. And that's maybe larger than you might expect. If you look at this typical 500 MeV case, then you have something like, yeah, I don't know, 500 keV per nucleon width of the span, so 250 keV per nucleon uncertainty in your N2lo calculation. Maybe you would want it better, but if you are honest, this is kind of what the method can give you, including all of the sources that we've seen. And for us, this is quite nice. So we are super happy about that. So I'm absolutely thrilled that the interactions perform that well and that the many-body methods perform that well, and that we don't have uncertainties of plus minus 2 MeV per nucleon, which you might have in the old days. So this is quite nice, but it might be surprising if you are used to kind of other views at this problem. Okay, you can do the same for the oxygen isotopes. We looked at them many times before. Now you can do the same with these uncertainty bands. And you can do the same also for spectra, because if you do NCSM, you often look in spectroscopy directly. And here I just show the uncertainty bands due to the interaction. So just this chiral interaction uncertainty from the first step. And you see this is quite interesting. It's really strongly dependent on the state that you're looking at.
Okay, ti chiederò quest'ultima cosa. Se io faccio una nuova richiesta di assistenza.
Oops. Could you? Okay. Some states are super stable. They have very small uncertainty bands, like this low-lying 2+ state here. Some states have huge uncertainties, like these guys here. And so now you see it's not just a very gross statement. You assign 2% error to your states or your excitation energies? No, something that really depends on the structure of your state. And in many of these cases, the cases that have big uncertainties, we actually understand why that is because of the specific structure of these states. They are super sensitive to individual features, individual terms of the interaction, and therefore react strongly to this order by order sequence in the calculations. Okay, good. Maybe I stop here. I think there's one more question in the chat that I kind of overlooked. So let me read it. Basically, you are fitting CD on the heaviest nucleus you can study at high precision, correct? Yes, so I think I would say we can also study calcium isotopes with pretty good accuracy. I think oxygen 16 we picked because this is the nucleus where all of the many-body methods that we have available can be applied. So also the straight NCSM calculation is possible there. So we are really, really sure about the performance of our many-body methods for this mass number. And therefore, it is for us a good choice. So you are right, essentially, with your question. We are pretty safe and sure about the precision of our oxygen 16 calculations. So we pick this as a reference point for the determination of CD. But I mean, the result wouldn't really change if we do the same story for say calcium 40 or so, because that's also automatically or by accident very well reproduced at the same time. Yeah. Okay, are there more questions?
I would like to ask you, I mean, to understand a little better, say, because your first, you said you started when you, for this quantification of errors, your first source of error, if I understand, it's really linked to the expansion itself. I mean,
yep.
So in a sense, so I was puzzled now by this final result that you showed about excited states.
Yeah.
Before you said that you expected the excited states to be in a sense easier to calculate than the ground state energy.
Yeah. Yeah.
And I didn't understand very well how this is linked. I mean, this uncertain. And also, final point. In the beginning, in a sense, it looked to me rather, rather optimistic as a result that you got from this first stage. But I wonder if one should interpret it in the way, well, now McClyde can retire. I'm joking, of course, in a sense that they expect something more, because this is over, I mean, in a sense, say, well, I've estimated the effect of the other orders, and so what should I expect? Say, I can go, just if you can help me to understand.
Yeah. Very good points. So regarding excitation energies, your first question, I mean, excitation energies are typically more stable with respect to the many-body convergence, with Nmax convergence in an NCSM. But the typically is important because the states that show up with large errors here, these are also the states that show sometimes a pretty slow convergence. This is, however, not shown here at all. This is just the interaction uncertainties, but still these things are connected. Slow convergence means that the state has a very, very complicated intrinsic structure. You need lots of basis states to kind of represent this structure appropriately. And that often goes hand in hand with a strong sensitivity to aspects of the interaction, because there is a particular orbital structure, orbital angular momentum, spin structure, which is sensitive to tensor forces, which at the same time is difficult to converge these things. So this is related. But you shouldn't forget, when looking at this picture, we're talking about completely different scales here. So if you look at the absolute uncertainty, and these bars look big, but that's also due to the fact that this is kind of a very zoomed in part of the spectrum. It only goes from 0 to 5 MeV. And still this monstrous error band here is only plus minus 800 keV. And this is for a tricky state. I'm happy with this. So I wouldn't be shocked by the apparently large sizes. I mean, this one is another bad guy, if you like. We know this state for a long time. It's the 1+ state in carbon-12, which is super sensitive to the three-body force. It moves all over the place if you switch off the three-body force. So it's expected that this one reacts sensitively to higher orders. So this is from N2lo to N3lo. The three-body force gets much more complicated if you go to N3lo, and the state reacts to this and moves. And it moves in the good direction because experiment is up here. So I think one has to look really into more details here for the spectra. The other point, I think one thing is not understood right now. So we are far from done, not the right time to retire, because I didn't estimate or even try to estimate the uncertainty resulting from, let me go back just a sec, from changing the regulator scheme. I don't know how to do that because it's really a different design choice at the level of your interaction. But this is something which we are worried about and which we want to understand. And we are working very hard with, in particular, Evgeny Appelbaum, the Bochum group, who have another family of interactions, which is in principle as nice or nicer than the non-local ones that we used. These are called semi-local interactions, don't want to explain it, but they have the same kind of problem like this one here. But they are really very carefully crafted from the point of view of chiral EFT. So you really want to understand where this difference comes from. Formally, the semi-local stuff might be superior. So from the basic wisdom of chiral EFT, you might want to prefer these local or semi-local regulators. But we don't understand why this difference is here. And this is something we are really trying to find out now. And I think for me, this is super nice. This is excellent for practical applications. We are ready to go with this. But there are still pieces missing in our basic understanding of effects and sensitivities at the level of these interactions. So there is still a lot to be done. And this is why there is this big question mark here.
Thank you. But before you answer the question on the chat, this says the answer concerning this spectral result, isn't it in a sense alarming? Because when you make a calculation of a spectrum of a nucleus, you cannot expect that all the time you do this very careful, say, error analysis state to state. I mean, I just wonder if, I mean, you come out and you predict spectrum of a nucleus, then in a sense, now I'm talking about comparison with experiment, not about, this in a sense is somewhat alarming for an experimentalist, isn't it?
No, I would say it's alarming if you don't want to do this uncertainty estimation. I mean,
you have to do it, but I'm saying practice. I'm just saying it's very beautiful. Yeah. I'm saying, no, it's fantastic.
No, I think
I wonder if you can always do it.
Yeah, I think, I mean, you will build some little, some experience, I would say, with what to expect. And I mean, from looking at these spectra, these are light nuclei. Each of them is a beast and a beauty in itself. So there are lots of discussions, lots of papers, for example, about boron 10, the spectrum of boron 10, the features of the interaction that you need to even describe the correct ground state spin. This is non-trivial. Many interactions get this 1+ state here as a ground state of boron 10. So it's known that these nuclei are very, very tricky, very subtle in the properties of individual states. So it should not be surprising at all that you see rather large uncertainties. It's kind of comforting because you know that your experience from the past with a random selection of different interaction matches to this observation in a more systematic fashion. I'm not shocked by that. I'm not worried by that. And I mean, if you just search for NCSM papers on boron 10, you will find 10 or so different ones which discuss the problem of this 1+ state. And if you go higher in the spectrum, it doesn't get better. Similarly, there are papers that discuss the problem of this 1+ state. So it's these are known suspects, if you like. So I wouldn't be shocked. I mean, I would be shocked if I see suddenly large uncertainties in, say, a mid oxygen isotope 2+ energy or so. I would expect these to be pretty robust and small uncertainty. Otherwise, I would worry. But my basic message would be, you have to pay this price. You have to go through this in order to make a really rigorous comparison to experiment. Otherwise, you never know whether to blame something on your interaction, to blame something on your many-body calculation, or to blame it on experiment. I think it's really necessary if you aim at this kind of precision. Okay. What attempts are required to reduce these uncertainties? Second, shouldn't these results converge with respect to the higher order interaction terms like N2lo? Are there no uncertainties in experimental data? Okay, if you take this plot, the uncertainties in experimental data are probably the line width of my little bars here, because this is spectroscopy data. You can do that by gamma spectroscopy, which is ridiculously accurate from our point of view. So we can, for these observables, forget about experimental uncertainties. It's different for other stuff. We just had a very nice work for lithium-6, a very light nucleus, and M1 observables, magnetic dipole observables, where the experimental and the theory errors are really on the same scale. There are other examples, like if you take carbon-12, this nice 2+ state here, and you ask for the quadrupole moment of this 2+ state. This is a sad story, because the experimental value on that, I think it's from the 70s, the original one has ±50% error bar. And there are new measurements which are very tough, very difficult to analyze, which try to get that experimental error down. We can predict this quadrupole moment for this state with an accuracy that's an order of magnitude better than experiment. So this thing about errors is really interesting, also if you discuss with experiment. Now, your initial point with reducing these uncertainties and higher orders. Yes, in principle, the path to reduce uncertainties is clear in all the different methods. For chiral EFT, it means go to still higher orders. Maybe you have to go beyond N3lo, the level we are at now, for certain observables. If the dominant uncertainties are from the many-body treatment, then yes, you have to go to larger many-body spaces, better many-body methods. It's a question whether you can practically do it. Even the step to N4lo will be extremely difficult, because at N4lo, the 3-body force kicks up something like 7 or 8 or 9 additional constants, additional parameters that you have to determine. And you've seen how laborious it was to determine just 2 of them. If you have 8 or 10, this is something which really requires a different approach. So it will be getting difficult to go much further in the chiral order. But in principle, this is the way to go. And with respect to should they converge, I mean, you've seen a very nice convergence for the ground state energies. There you really had a very systematic nesting of these bands. That's what you want to see. Here for the excitation energies, sometimes, sometimes not. So sometimes the bands are getting smaller and are compatible with each other. Sometimes the bands seem to get a little larger. I mean, grosso modo, so looked over a large sequence of different orders, yes, I would expect to get the uncertainties systematically smaller, but it doesn't have to happen in each and every case. And again, something like this here, it's obviously a good thing to go to N3lo, because the description in comparison to experiment is drastically improved. But since you change from N2lo to N3lo quite a bit, this N3lo error is comparatively large. And that's to be understood, because you've changed in between your 2 highest orders quite a bit in your prediction of the observable. Okay. More questions?
Well, only to recap, because we already perhaps mentioned this with the oil state in carbon. So of course we expect let's say the simple no-core model without any in medium and so on to be better, as long as we can reach an I enough, let's say,
yes.
And max or whatever. I mean the convergence. Okay. So the problem in that case is just that with the, let's say, in principle precise calculation, we can get far enough. Right? Okay.
Yes. This is you formulated this very well, but it's really in principle. So if you think about this first excited 0+ state, the whole state, it's impossible in practice to converge this in the no-core model. I mean, it has been shown that if you take from a cluster model a state which has this alpha cluster structure that you expect that you need for the whole state, and you simply expand this cluster state in an harmonic oscillator, no-core model type basis, you need something like nmax 50 or so to represent this clustering adequately. We will not be able to do nmax 50 with no trick whatsoever. So there will always be situations and particular states where you, for example, have this basic mismatch in the basis functions that you use. And in order to treat them, you will have to go to a different scheme which uses different basis functions.
Yeah, okay, thank you.